So might as well get started with why do we care about manifolds? Taman, you want to start?
Sure. I mean, we care about them because we care about sets that have some defined notion of continuity, because that's how the real world works. Points are related to each other in some manner. So they're not just a set with no order established, and a manifold does that. And then we care about topological manifolds specifically because locally they're isomorphic to our Euclidean plane, or at least one Euclidean space, and that's the space we happen to live in. So we like that very much.
Mm-hmm. There's just one thing I want to like clarify that you said. So you said we care about manifolds because they give us a notion of continuity. Is that what you said?
Yes.
So do we need I guess it depends on how you define a manifold, but do we need manifolds to define continuity, or just like topological spaces?
That's fair.
Okay.
Yeah, so specifically with a topological manifold, then yeah, a topological space gives you continuity already, but then a topological manifold gives you one where you can sort of relate it to your world.
My like the way I understood manifolds is literally just spaces that resemble Euclidean space locally. And this is like I'm not actually exactly sure why topological manifolds are useful, but I do know that like differentiable manifolds are useful because they increase the like amount of spaces we can do calculus on, which is obviously very useful.
I mean, all manifolds are topological spaces. I think he just said
what to say
manifolds, but he means manifolds.
Sorry, say again. All manifold? No, okay. I know what you like. I know what you mean, but like a topological manifold is kind of
it's like a for the word manifold. It's not.
Oh, is it really? I thought there were more. I thought there were more like I thought there were stronger definitions of manifold, such as like a smooth manifold.
I mean, there are. I mean, in my head, it's kind of like Venn diagrams to me. Like you got the big circle of topological manifold, then you have d-dimensional manifolds, and then in there you might have smooth manifolds or differentiable manifolds, and it keeps on getting smaller. You're basically classifying the sets pretty much.
Right, but so like my I guess thing is that I can see why like a smooth / infinitely differentiable manifold would be a useful concept. And I can see how it'd be useful because it allows us to do like a certain kind of math on a larger like range of spaces, right? It allows us to do calculus on a bigger range of spaces. But what exactly? What the like? I don't know much differential. Like I don't know anything about differential geometry, but that's just the impression that I got. But with like topological manifolds, I can see I can see how I can see this. I can kind of understand the significance behind having a space that locally resembles Euclidean space, but it's just I haven't seen like concrete examples of that being applied.
I think that you have secretly seen some examples being applied, specifically when it comes to coordinate systems. I say any coordinate system transformation that's ever existed is secretly written in the language of topological manifolds. So for example, you've probably already gone from Cartesian coordinates to polar coordinates before. If you're a bird and you're in the real world and a human is like an engineer, engineering the fucking whatever the thing away, you don't care if it's like Cartesian coordinates or polar coordinates. So that's the chart. And so we've been playing around with manifolds or with charts this entire time, going from chart to chart. Like maybe we decide to double the basis vectors or something like that, or choose a completely different chart. Would you agree / disagree?
You're just describing vector spaces.
I mean, am I?
The moment you said basis, that's
okay. Forget basis. That was too advanced. Yeah. You're right. You're right. Forget I said basis. Let's say intuitively, hand wavy, you got like polar coordinates, whatever other kinds of coordinates. Like you're basically mapping the real world onto a chart where you do math on it. Or at least that's what I feel.
I don't know. I mean, I'm just speaking from my experience with like multivariable calc, where you do have like the like change of coordinates, and then you like do your like integrals differently based on which coordinate system you're in. And there's like ways to like transform your integral depending on the like transformation of coordinates or change of coordinates. But that's still like Euclid. That's still like it's still Euclidean space, and it's not like at least my experience with it was still with like Rn and not any other like topological manifolds.
Topological manifolds have to be Rn. No.
They have to be homeomorphic to Rn, or like they have to be locally homeomorphic to Rn.
Yeah. You're right. Yeah.
Or to subsets of Rn.
Have you worked with geometry on a surface of a sphere before, perhaps? Like where triangles can have 39 degrees and such?
Like I've like read about it, but I haven't actually like worked with it.
Wait a sec. Isn't it that to have a topological manifold, the topological space needs to have the standard topology equipped?
No.
Any topology?
Yeah, it's any topology.
Okay. Cool. I was under wrong impression then.
Wait, so I think it might have to be standard because it's not just any Rn space, it's specifically Euclidean space.
So he was asking about the topological manifold itself, not the thing it maps to.
Yeah. Like the topological space that is whatever. By the way I think of a topological manifold, is I think of it as a property of a topological space, because it doesn't add any structure. When you look at the definition of a topological manifold, it says for all P there exists. Yeah. It doesn't actually add structure. It doesn't say a topological manifold is a topological space equipped with an atlas. It does not say that. It just says that this exists. If it does exist, then the object you're looking at is a topological manifold. It like classifies the topological spaces.
Yeah, I can see that.
Okay, cool. Might as well start off with what is a manifold? The official definition. Taman, do you want to try explaining that?
Sure. You can map any open sets into open sets in Euclidean space. Those maps are invertible. For every point you can map, it's a neighborhood containing it into an open set in Euclidean space. That map is invertible, and the inverse is also continuous, which then applies the map going forwards is continuous.
And the map is also continuous going forwards.
Yeah.
And backwards. Yeah. Any idea as to why? Why it has to be invertible? Why it has to be continuous?
Because that's like sort of the whole point of why we're doing this.
Basically, like that condition for a map, the like technical name is a homeomorphism. And what it
are you sure about that?
Yeah, a map that is continuous, invertible, and has a continuous inverse is literally a homeomorphism.
Okay.
So basically, if it weren't defined like that, then like the whole reason a homeomorphism is defined the way it is to kind of say that the two spaces are the same, or like the two like open sets are the same in some sense. So if, for example, the map didn't need to be invertible, then you could just map all of the points in the open set into just one point, right? And then it wouldn't be invertible, but it also wouldn't retain any of the structure that we wanted to retain. And that map would still be, if you take like some subset of like a torus and you map it to just one point, let's say 0, 0, that's a continuous map, but it's not invertible. Yes. And because of that, it doesn't fit the definition, and it makes sense that it wouldn't, because it doesn't retain any structure. And it doesn't retain any of the structure we wanted to retain.
I mean, I can say that it retains structure though.
How? You take
what? You're losing data.
Yeah, you're losing, like you could take like any subs, you could map the entire torus to one point in Euclidean space, or you could map any like open set of the torus to that same point, and it would give you like basically like the same result or image. Whereas if you were using the definition of a homeomorphism, like if you require that the map be be a homeomorphism, which just means it's continuous, invertible, and has a continuous inverse. If you require that, then you cannot define a homeomorphism between a torus and like R2, right?
Okay.
So
I
like,
see what you're saying.
Like that, like what I'm trying to illustrate is like kind of like what Taman said, where homeomorphisms preserve like a specific kind of data about the space, which we might call it's I mean, this is kind of getting into like algebraic topology, but you know, kind of like the number of holes in the space.
If we recall from 2 weeks ago, when we had isomorphisms on sets, and then those preserved a certain structure on the sets, which was specifically cardinality, right? In this one, homeomorphisms is the fancy word we use for isomorphisms on categorical and not topological spaces. And in this case, the structure we're preserving is that sense of continuity. And then as for why we define it that way, it's because we want to work in a space where things are continuous. Therefore, we say that we only care about it if it's continuous.
What do you mean? Yeah. What do you mean? What do you mean by the structure we're preserving is continuity?
As in, okay. So with a structure, you have what is called your ground set, which is the set from which you take all elements, right? And then after that, you have a series of relations, a series of functions, then a series of constants. This is called
what are constants?
Signature. Just like have you done group theory? Or a little bit?
I've done a bit of group theory, yeah.
Nice. So in group theory, you might imagine your constant, the only constant to be the identity, right? Like the special thing that you put there.
That all sets have, like in this case, like all topologies contain both like the empty set and the entire set. Would that be a constant?
That would be a property of the actual relation itself. So you could define like the unary relation on the subsets, on the set of subsets of the actual set itself.
Okay.
Like this subset is in here or it's not in here, and that's your unary relation. I'm not too sure what the type signature of this would look like, but I'm imagining you would have some function. Would you have any functions? Because on a group, you would have your binary functions. So your one binary function, and then your one inverse function, right? But I'm not too sure about a topological space, but essentially when you map from one structure to another, you preserve every single relation and function. And if all of those are preserved, then that's called an isomorphism. In this case, our relation for the topological spaces is that relation of continuity or open sets, right? Like whether or not a set is open. And that's,
yeah.
And then if that sense is preserved, then it's an isomorphism.
Okay.
I'm not doing a good job of explaining this.
Yeah, like I guess basically for every open set in like the like domainer preimage, there would be like a corresponding open set in the image, and that's kind of the structure that's being preserved. Maybe that's one way to think about it.
I have a question. So all of this theory was developed in hindsight, specifically when applied to physics, was developed in hindsight to fit a specific model that already existed. And so I ask, why did they define it this way? Why did they define it in terms of homeomorphisms between open sets?
Because homeomorphisms are isomorphisms, and then we just build structures. Because like, think about how a group is defined, right? What do you care about intuitively?
I don't know about group theory, unfortunately.
Okay, sorry. But like with a group, you build it on top of the notion of symmetry, right? And what's the only thing about symmetries that hold across all symmetries? It's associativity, right? Or well, inverses too, but associativity and inverses. So you build a group using just that, and now you define that to be a group because you isolate all the properties you care about, and then you bundle it together, and now that's called a thing, right?
Yeah, like now, David, the important thing to take away from what Taman is saying, even if you don't know anything about groups, is that two groups that are isomorphic are basically exactly the same from the perspective of group theory. Like they contain the exact same data, and they're like basically completely interchangeable. Like you could do the same things with one group as you could do with another if they're isomorphic.
But at the same time, there are properties that are true for charts that would not be true for the global world, for the thing you're charting. The first one that comes to mind is differentiability. Continuity is preserved, but you can have something that is differentiable, like a differentiable chart, whatever, for one of the charts, and then it's not differentiable for one of the other charts.
But
like
that doesn't matter though, because that's not something we care about preserving.
Okay, so in this case, so when you're talking about groups, whatever, they're basically the same. You're talking only about like continuity in this case. You're not including other properties.
Like okay, like actually with like isomorphisms, it might be like a bit different, because with isomorphisms, the groups are like the exact same, except like the elements are maybe have different names.
No, homeomorphism is isomorphism. It's just, they're synonyms when you're talking about, like isomorphism is a big concept, and then for every structure, or almost every structure, you just have a different name for an isomorphism on that structure. Like if you think of your metric spaces, you call isomorphisms isometries. If you think of topology, you call isomorphisms homeomorphisms.
So I've got like a mental block right now, which is stopping me from understanding this explanation. I'll try explaining it to you guys, and maybe you guys can help me clarify this. So my idea is that if you have like, this is your original world that you're trying to chart, and you have like a chart here and a chart here, and they happen to intersect. So whatever, you chart it here, you chart it here. One sec, let me think. Oh yeah, so the reason why the maps have to be invertible and continuous is, suppose that this transformation is, this one over here is for Cartesian coordinates. So you take the real world right here, this house, and you represent it with Cartesian coordinates. And then this one over here is polar coordinates. The reason why the maps have to be continuous and invertible is because suppose you start over here in Cartesian coordinates and you want to switch over to polar coordinates. Because of the fact that these maps are continuous and invertible, it means you can go up to here and then back down to here. And basically it affirms the fact that you can switch coordinate systems because of the fact.
I wouldn't, that is a consequence, not a reason.
Okay. Okay. Interesting.
Like
would you say
I would say so even if it's not invertible, like you might still be able to define a map directly between the two charts without having to use the inverses, right?
Interesting.
So that's not like kind of like 10M said, it's not a reason, but more of like
a consequence, a very nice consequence. Do you think that, in my head, this is the reason why physicists defined it this way, because of this nice property? You don't think so?
Imagine, for example, I take your little intersection thing. I define one map X that maps to the origin. Then I define one map Y that maps every single point to some point 10, 10, right? 10, 10.
Okay.
Then between the origin and 10, 10, I can define an invertible map between them. Specifically, the map that takes 0, 0 to 10, 10, and then the inverse that takes 10, 10 to 0, 0. And there you go, right? And
I'm not exactly sure what you're saying
to do that.
Like, wait a sec. What I'm trying to say is the psychology here. I don't know. I like to understand why these early physicists decided to define things the way they did. And to me, the biggest property that they enjoy of topological manifolds is this property here. That basically
the thing is, like you know so little about topological manifolds that there's probably and same for us, or I don't know about Tana, maybe you know a lot more than we do.
No, absolutely
not. But yeah, like all of us, let's just say we know next to nothing about topological manifolds. There's probably like a bunch of other reasons that we just aren't aware of or aren't able to understand right now that it was defined this way. It's very unlikely that this is the main reason, or like that having like chart transition maps is the main reason why like charts were defined in terms of like homeomorphisms.
And
okay, I see.
On that note, I would severely doubt if the person who defined this was a physicist at all.
I mean, we can check.
Maybe
that's something checkable though.
Yeah. I recall him mentioning in the video that it took Einstein years to understand this properly. In terms of space-time, like understanding what is happening, like how can you represent space-time mathematically?
The term manifold comes from the German Manig, weird German word by Riemann, Jana, this was not a.
Yeah. I'm sure manifolds existed beforehand, but I guess it's something that like physicists kind of stole to apply to. Okay, in that case, yeah, there are other uses for manifolds. Okay, fair point. So it's a nice property, not something that's defining.
Right. So
was it
essentially,
Riemann?
it
Didn't
was
Riemann? Sorry. Yeah, go ahead.
No, I was saying that it was way back in the 1733, some mathematician was studying like non-Euclidean geometry, and this is like before the time that they knew space-time was curved. So back in the day, like all of Newtonian physics is Euclidean geometry, right? So this was like just math guys doing math stuff, not. And then later,
but what is interesting is that the like geometry that people use for to describe space-time, which I believe is called semi-Riemannian geometry, is actually like no one really cared about it in the math world before they realized it was applicable to physics. Before that, like people just used like Riemannian geometry amongst other geometries because it had like I believe more interesting or like nicer properties. So like semi-Riemannian geometry, which all of like general relativity is based on, is actually kind of like or was a more obscure part of math before general relativity.
So it's kind of like the physicists were in their their mathematics shop, and they were looking at other papers. They're like, oh, interesting, we got this one. They're like, this one over here, I like it a lot. I think we'll use it for all of physics. Like, do you think that's what happened? Like the math already existed, but was very obscure, and then physicists kind of built off of the math that already existed?
Yeah, like I'm sure like physicists further developed the math, like the math itself. But
yeah, true.
More often than not, like physicists just steal stuff.
Yeah.
Which isn't bad.
Physicists.
Yeah, that's not a bad thing. Yeah.
They're gonna go to physicist jail. That's what's gonna happen. Anyways, so yeah, it's a property, not okay. That clears things up a lot for me. Although I still feel like a very crucial part of this entire manifold stuff is coordinate transforms. Like whenever I translate theory into things that I've done personally before, I feel like coordinate transforms is something where it's like the essence is basically what's happening with manifolds.
That's an interesting perspective, but I'm fairly sure the canonical way to think about this is there are structures, then there are isomorphisms between structures, and it just so happens that isomorphisms here have that nice property.
I see. Okay, cool. All right, so that makes sense. Now I feel I understand the manifold pretty well, so we can move on to examples of manifolds.
Honestly, I don't.
Oh yeah. We can pretend that we understand. In reality, we don't, but I can Dunning-Kruger myself away. So here, I think a good idea is that we go over one example each of a manifold and explain like why it's a manifold, whatever, using the definition. So like one of us takes a circle, one of us takes like a whatever, that type of stuff. Okay. So I can get started with, I'll pick a difficult one. Let's see. I'll pick a sphere. How about that? Try to explain the sphere.
Sure.
Or yeah, here you go. So first thing first is that I need to craft a topological space. And to craft a topological space, I need a set and a topology. So first thing I'm actually going to do is I'm going to craft my set. What I'm going to do is I'm going to start with R3. So just space. And then I'm going to use restricted comprehension. I'm going to say, let's see, I'm going to say, I want the tuple X, Y, Z that is a part of R3, because this is what restricted comprehension says. You need to say where it comes from. Given that X squared plus Y squared plus Z squared, blah, 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 blah. Okay, yeah. So basically I start with R3 and then I chip away at the space until I'm left with the sphere. Kind of like those sculptors or whatever that craft these statues. So now I have my sphere. This is just a set. There is no order implied. In fact, I can't even visualize it, because to visualize it, I need some sort of structure. Then what I do is I equip it with the standard topology, basically craft a bunch of softballs, whatever, all these open sets. Now I have a topological space. Now, what I need to argue is I need to show that this topological space happens to be a manifold. Specifically, in this case, it's a 3D manifold and a 2D manifold. It's got both.
How's it a 3D manifold?
Because the sphere originates from R3, so you might as well, like, it can be represented.
No, but the space itself is 2D.
Yeah.
Like the sphere itself is a two-dimensional like surface.
Yeah.
Like you could say you could define a circle in R3, but it doesn't make it a three-dimensional.
What if I did this? It depends if I did greater than 1 or equal to 1. If I did equal to 1, then I agree with you. That would just be the surface, and that would have to be.
Sure, if it's less than or equal to 1, then it would be strictly.
Oh, yeah, you're right.
If it's less than or equal to 1, I'm pretty sure it'd be strictly a three-dimensional manifold.
Really?
Not
I disagree.
Okay.
I'll try to prove. I'll try to do like a very hand-wavy proof.
Let's do it.
Okay. So the idea is, first what I do is now oh my God, yeah. No, wait. I equip R3 with the standard topology. I cannot equip the sphere with the standard topology. That does not make sense. What I need to do is equip R3 with the standard topology and equip the sphere with the subset topology. Basically, what happens is I take all of the open sets and take the relevant intersections, which, okay, whatever. You can maybe visualize that. And so now we have the set equipped with structure, which is the sphere equipped with the subset topology on the sphere. And now I need to show that it's a 3D manifold, which we can probably intuitively agree on.
If it's a solid sphere, then yes.
Solid sphere.
Yeah.
Actually, even if it were a solid sphere, can we be sure about that? Because you can still have a point on the surface of the sphere. Whereas R3 has no surface boundaries.
No, as long as it's less than, it's homeomorphic to R.
Oh, right. Because
to R3.
Open. Right, because it's going to be open.
Yeah.
Gotcha. Yep. No, that
okay, cool. Yeah. Yeah, you might as well just have one chart for the entire thing. You know, like instead of having a series of charts, you just have one chart for the entire sphere. Yeah, cool. So that's a 3D manifold check. Now for 2D manifold, this one I'm not sure I'll be able to prove. I'm reasonably confident, but the idea is you have these open sets that include the surface, because you take the intersection, right? The intersection means that you includes the surface as a part of the open sets. Oh, fuck. I think you're right. Wait a sec.
Is there even a surface if it's less than?
No, yeah, there's
no, but if it's a less than, there's no point. There's no like final edge point. You can only get infinitely close to it. But there's
there definitely is. There is, because of the definition of the subset topology. What happens is you intersect each open set with the sphere. I guess in this case, it's S3, which means the intersection will include the boundary.
But what I'm saying is the boundary is not part of the set here. Like the boundary itself, which is x squared plus y squared plus z squared equals 1, is not part of the set. So if you do less than or equal to, then yeah. But in that case, it's closed, and so the like entire space itself would not be like homeomorphic to R3. But I don't know if that matters. You could just do less than or equals to.
Yeah, I did less than or equals to. That's what
like it would still like what I'm saying it doesn't matter. When I'm saying it doesn't matter, even if you make it less than or equal to 1, it would still be a 3D manifold. That's what I mean by that.
Okay, cool. But is it a 2D manifold, less than or equal? I think yes, because the Earth is. That's literally what the Earth is. Like
the Earth's surface is a 2D manifold.
Yeah.
But the Earth itself is a 3D manifold.
Right.
Why?
Let me explain.
Yeah, okay? Go ahead.
I'll
hand wavy proof, annotation.
Please. Yeah, hand wavy.
Thank you.
Okay. So let's look at like a cross section of our sphere, which would just kind of look like a circle.
Sure.
From our perspective. But this is just easier like right now we're looking at like a cross section of our 3D Euclidean space, okay? And we want to take and we want to like find an open set in the subset or subspace topology, right? So we take some open set of the Euclidean space, and this would, can we agree that this, assuming it's assuming like the like this square, assuming there's like if this is like 1, 0, we will say that the square doesn't actually touch 1, 0. It's still open, right? And in fact, this is a cube. We're just looking at a cross section. Actually, maybe it would be even easier if we just do 2D, okay? Because it's kind of the same thing. Like if you believe that a sphere is both a 2D and a 3D manifold, then you should also believe that a disk,
a disk circle.
is, you should also believe that a disk is a 1D and a 2D manifold, right?
Oh shit. It's probably not a 1D manifold.
Yeah, it's not. And like the reason is, like, roughly speaking, that you can't define
a map between, like,
I really hope I'm right when I say this, because I might be wrong, but
I
don't think you can define a homeomorphism from like an open set of R3 to R2. I don't think you can.
What if you just map it to the what if you just map it to the empty set?
But that's not a homeomorphism. No, it could be if it's to the empty set, it's not continuous either. But if you map it to like one element, it would be continuous, but not a homeomorphism.
Yeah, because not invertible.
Interesting. Okay, I see. I agree with you. I mean, so a sphere.
There's a fairly easy intuition for all of this stuff.
Sure.
If you imagine, if I'm standing on the surface of a sphere and you zoom me in really, really close, then I couldn't tell the difference between it and the 2D plane, because that's why there are flat earthers that exist, right?
Mm-hmm.
Therefore, the surface of the sphere is homeomorphic to.
But if you're in the middle of a sphere and you zoom in, it's still 3D.
Exactly.
Okay, that's cool.
But a sphere is not like a sphere is not a ball, right?
Yeah. When we say manifold, we mean like a it's not like filled in on the inside.
Oh, yes. Okay. Yeah. I see. Just the surface. So in this case, instead of less than or equal, it would just be equal.
Okay, here's the thing. If you take an intersection, let's say this is R2.
Yeah.
If you take an intersection like we do here, like this bit, like this thing right here, this is an intersection of an open set in the standard topology in R2 and our disk, right?
Sure.
So this blue section would be an open set in the subspace topology on the disk, right?
Okay.
So now I want you to find an intersection with an open set of R2 and the disk that only contains the boundary. And if you can't do that, then you can't say that it's a 1D manifold.
Yeah, you've proved that there exists a map that
like with the circle, if you take an intersection, you can get that it's only the surface, right?
Okay, makes sense. Okay, I agree. So who wants to do the next one of a donut potentially?
You zoom in on the surface really close and it looks kind of flat. So therefore
it's a 2D manifold. Okay, sure.
Okay, here, let me ask you guys a different one.
You want me to share the whiteboards?
Yeah. Cool. So like we have like in the video, he explained why this is not.
That's the one I was going to bring up. Yeah.
Yeah, he explained, like we all saw the video. We kind of understand why this is not a manifold. But how about something like this? Is this a manifold?
Yeah.
Yeah.
Yeah, I think so. Yeah.
Yeah.
It's not differentiable.
Yeah, that's the thing. It's not differentiable because it has cusps.
Yeah. It's not smooth.
Yeah. So yeah, it's not a smooth manifold, but it is a manifold.
Or is it?
It highlights the difference between the difference between topology and geometry almost.
What about here?
This is like it depends on what you think it is. So if you think it's closed, then like this part here would not be, actually it might under the subspace topology be considered like homeomorphic to a subset of Rn, but I don't think so. So if you think it's open, then it would be homeomorphic to a subset of Rn. And if it's closed, then it wouldn't.
Okay, cool. I've got a tricky one for you guys. Suppose you have a discrete space. So just a bunch of dots, whatever. What kind of topology or what kind of manifold is this? The more you zoom in, the more dots there are. It's discrete.
What do you mean by that? The more you zoom in, the more dots there are.
If you zoom in, you'll just like get more of these, like this. Like it's discrete space. Actually, I'll just mention it right now. You guys say if it's true or false. I argue that this is a zero-dimensional topological manifold. Because eventually, the more you,
Are there countable dots or uncountable?
Uncountable.
That wouldn't necessarily be uncountable. How would you arrange uncountably many dots in a discrete manner? Is that even doable? Yeah, actually.
I don't know. No idea. Yeah. Just suppose this structure exists. I don't know. It's an idea, because the idea is eventually you zoom in and you reach a dot, which is 0 dimensions. And so you literally get a 0-dimensional manifold.
Well, here's the thing. I think the way David's describing it, you can, because he says the more you zoom in, the more like dots appear, right?
I can probably define an ordering on that though, right?
Yeah, you probably can.
Yeah, so then it's not uncountable.
But do you know about the like well ordering theorem?
Okay, no, I know what you mean. No, I mean, yeah. Okay, no, I mean, rather than that, you know how to define an ordering on the rational numbers, right? Like you arrange them in a grid.
Like I can kind of do it if you really ask me to.
Right. Yeah, you do the grid and then you go diagonally. I can imagine I guess a similar argument for this.
With this,
like,
interesting.
I go the 9 by 9, like 3 by 3, like 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay, I see what you mean by ordering. You mean like a bijection to the integers.
Exactly.
Okay.
So this is a 0-dimensional manifold?
No, because a 0-dimensional
it's a countable setting.
A 0-dimensional manifold would have like sets homeomorphic to R0, which
is a dot.
Like what is R0? Is it a dot or is it the empty set?
A point.
I mean, I think I have this. It's either the empty set or the set containing the empty set. I can't remember which. It's one of the edge case definitions. But
anyways, I feel intuitively it feels like a 0-dimensional manifold.
No, it wouldn't be, because then it wouldn't be invertible.
Because look, you have multiple dots in like the image, or sorry, pre-image, and your image is either the empty set or just one element.
Yeah, the set can either 0 or 1. Doesn't matter either way. It's a singleton, right? So.
Okay, fine. It's not 0-dimensional. I mean, I'll search it up. Is discrete? This is discrete space, no?
But like discrete space is like a pretty broad term. Yeah.
Okay, fine. I guess it's difficult to define what discrete space is.
Wait, I don't think you even well defined it there, because we couldn't even establish like a cardinality on that. Right?
What's a cardinality, by the way?
How big the side? Yeah.
Yeah.
Okay, cool. Yeah, so like any discrete space is a 0-dimensional manifold. I guess it depends how you define a discrete space.
What? I'm searching it up. What is a discrete space?
Oh, maybe you just equip it with the discrete topology ? No, that doesn't make sense.
Apparently, discrete topology is a 0-dimensional manifold.
But it's defined differently than how you would imagine. Okay. In topology, a discrete space is a particularly simple example of a topological space or similar structure, one in which the points form a discontinuous sequence, meaning they are isolated from each other in a certain sense. The discrete topology is the finest topology that can be given on a set. Every subset is open in the discrete topology.
Nice. So that's a power set.
But I don't get how that's a 0-dimensional manifold.
Yeah, I don't see that.
Let me think. That means it's homomorphic to R0, which is literally just the empty set. Or
wouldn't it be subsets of it are homeomorphic to R0? But I still don't get how that's possible.
That means every single element is homeomorphic. Yeah, no, that's cool. You just have a one-to-one pairing to the empty set with literally everything, like all the elements, because it's the discrete topology.
Maybe like, yeah, maybe every open set maps to the empty set.
To the empty set.
But I don't see why you couldn't do that for any other topology.
Right. Because where does invertibility go? Is out the window or?
Yeah.
Fair point. Are all topologies zero dimensional?
No, that can't be right.
Yeah, no, I don't think so either.
But I wonder if there's like a way to define a topology so that it's like a manifold of multiple dimensions. Like you can define it as a manifold of multiple dimensions with the same topology. But I would guess no. I would guess you can't.
Yeah. I feel it's got to be only one of them. No, actually, no, I can probably prove it hand-wavily by saying manifolds are used as a classification on topological spaces. And for topological spaces to be homeomorphic with each other, they need to have the same properties. So if you have a 1D topological space and a 2D topological space, those are two different properties of the topological space, which means they'll never be homeomorphic to each other, which means they can't equal.
I understand now. It's not the entire space is not homeomorphic. It's every single open set is homeomorphic to an open set. But every single open set is the singleton of a single discrete point, whereas every single open set in R0 is your singleton containing the empty set. Therefore, you're mapping one thing to one thing every single time. Because it's not the entire space to the entire space, it's open sets to open sets. And all of the open sets are singletons.
What's a singleton?
No, but all of the open sets are also like, the open sets aren't, singleton is just like one element.
Yes.
Okay.
All of the open sets, they're not only singletons, they're also like unions thereof, right? So you could have like multiple elements in an open set, and now it's still mapped to like the like singleton in R0.
Right, but it would it? Oh yeah, because
there are multiple elements, right?
In any case, I think we should move on to finish.
Here's the thing. You could define a continuous map, but it still wouldn't be invertible even for subsets.
That wasn't the criteria though. It wasn't that every open subset maps to an open subset. It's that for every point there exists an open subset containing that point that maps to an open subset.
Yeah, you're right.
Therefore, for every P, there is the singleton that's containing P, which is open, and therefore that maps to our singleton containing the empty set.
I see. It's not defined, a topological manifold is not defined in terms of all the open sets. Yeah. It's defined in terms of all the points with neighborhoods around that point.
Now tell me why you can't do that for any arbitrary topology. Why only the discrete?
For any arbitrary topology, it is not true that for P, the singleton containing P is not an open set. It is only true for the discrete one, because that's how the discrete one is defined.
That's why it's defined, yeah.
Yeah.
Nice.
Because if we take another manifold, the intuition we have is that we take that point and it's like an open ball surrounding it, right? It's not just that point itself, it's that point and its neighborhood, and that's the open set. Whereas in the discrete sets context, the single point, its neighborhood is nothing. Therefore, the open set containing it is itself. And therefore that maps to the single.
Oh, okay. Sorry. I was just gonna, it makes like this, like I have the definition of a manifold written down. The second I looked at it, it made sense.
Nice.
Because I was thinking like why, there are other like open sets containing those points, but it just, all that matters is there's one, right?
Exactly.
There's one such open set. Gotcha.
Nice. Okay, cool.
The rest of the topics we have are just compose the functions and you can go back and forth between the sets. Nothing too much.
Okay.
But so, I think it's still like worth looking into why those are useful. I guess for coordinate changes, but are there any other reasons?
What do you mean for the rest of the topic list?
No, for the chart transition maps, mainly because 10M was talking about like composing like inverses and stuff.
Okay. So we move on to the next topic. Like, what's a chart?
Sure. Yeah.
Okay, cool.
We kind of covered it, but yeah, we can.
Yeah. Taman, you want to provide a brief explanation?
So a chart is your mapping function and the open set that it maps from in some ordered pair. Your U and your X.
Oh yes, that's right. It's actually a tuple.
Yeah.
I had a talk with Jacob yesterday. He's joining the Quantum Mafia, and he showed me how you can think of math as having types, being like a strongly typed language or a typed language, where like for every object you use, you can assign it a type.
Yeah, that's type theory.
Yeah, I know. I know for programming that was a thing, but I had no idea you could do it for math.
It's an alternate type theory is an alternate like foundation for mathematics that was proposed way back when, like versus Zermelo-Fraenkel, and then Voevodsky, who Russian mathematician, I think died like 2018 or something like that, fairly recent. The bulk of his work was extending that to something called homotopy type theory.
Oh, yeah, that's what you were talking about.
Yeah. Like this guy I was talking to like brought up homotopy type theory, and he basically said that you could use it like if you developed mathematics just based on homotopy type theory, then you can have computers like prove theorems potentially.
Yeah, have either of you worked in a computer proof system before? Like using computers to prove stuff? It's pretty fun.
Oh, no. Oh my God, but somebody recommended to me that I messaged a friend of mine, and he said I should check out Lean Prover.
Oh yeah. That's the one I've been learning on. Yeah.
Lean Prover.
Is it worth learning?
As of right now, I'm just having fun playing around, like learning all the they call it tactics, like basic commands.
Oh, cool.
Yeah, and it's pretty cool. Like I think recently I just did like what was it? Commutativity of natural numbers or something like that.
That's crazy though, that you can have a computer proof stuff like that.
Yeah.
And it did like could it work for like could it theoretically work for anything? Like any theorem? Like I know the Gödel incompleteness theorem kind of like prevents that, but just like could it work for like I don't know, some theorems and like Stokes theorem or something? Right. If you could define anything properly.
I think the key part to understand, it's not like magic though, right? As in you put in all the definitions and then you tell it at every step, like you have a list of definitions, then you tell it, okay, I want that definition expanded within this thing. And then I want to apply this theorem, which I proved before, to the expansion of that definition, and it just sort of does like pattern matching on it. Or if I have like a P and Q, I can tell it, okay, I want you to take that P and Q and split it into two cases. Then it like runs the two cases for you. But like you're still dictating every step what to do, right? It's kind of like automation with computer programs.
That's really cool.
You're coding, you're telling the computer what to do. Like it's not thinking for you in that sense. It
So
just makes things more efficient.
Okay, gotcha. All right.
And more formal because a lot of mathematics had to actually, like even today, has to be rewritten because it's like some guy proves something really cool and like 10 people prove really cool stuff based on that. Then the original guy's paper has a tiny mistake on it, and suddenly it's all panic. Is this salvageable, or is all that effort just down the drain because this error is crippling? Whereas a computer, a little bit more tedious sometimes, but also speeds up your work a lot of the time and avoids all of that error.
Mm-hmm.
Damn, that's dope. I'm gonna have to look into that sometime.
Yeah. All right. Next up is coordinates maps, and then chart transition maps. Oh, Adar, you want to try explaining?
Sure. So the way I understood coordinate maps is literally just taking like our homeomorphism like X and then splitting it up into the different into if we're mapping to Rn, you split it up into n maps, so one for each like point, or like one for each coordinate inner tuple. I didn't really understand, I see, okay, cool, but I didn't I saw like what it was. I got it, but I didn't fully understand why you'd want to do that. Do you guys have any idea why?
I thought of it in terms as your partial derivatives, I guess, even though your differentiability is not preserved, but it's like there are times where you want to look at the change in only one coordinate, or you just want to spread.
Okay.
Maybe it's also easier to define. Maybe.
Yeah, that might actually be like like the reason that it is easier, like that. Yeah. Like that's how you would actually define the map
in real life.
You define, like if you even saw the examples he gave with like he just defined the map for each coordinate separately.
Yeah.
So maybe it's just a way to clarify that, but I feel like there has to be more meaning to it than that. The partial derivatives explanation is interesting, but I guess it wouldn't be super applicable yet because like this is we're still in the realm of like topology.
What about from the like physics perspective, where you might want to parameterize something as a function of time?
Ooh, interesting.
And each coordinate,
I guess just have the option to access each coordinates, to do cool stuff with like each one, as you mentioned, like maybe take partial derivative,
maybe just like making a point that like the coordinate maps combined are equivalent to just the like map X. Yeah, and for
I was just saying, like if I was creating the total map X, I would do it coordinate by coordinate. Like you literally have no choice. But and then chart transition maps. That one we talked about a ton. It's like the idea of different coordinate systems glued together charts to form an atlas. So there's this idea of like the maximum atlas or maximal atlas or something, which is the atlas with all the possible charts. And then you can glue them together to form the original space. And then the really cool parts.
And how would you do that?
How would you
glue them together? I didn't get to that part in the lecture.
You go from one, you go back up, then you go down to the other one. It's what we were talking about earlier.
Okay.
With transition.
Cool. I'll just look at it after, I guess, but I can kind of intuitively get it.
Cool. And there's the really cool idea of like the entire philosophy for manifolds. Like, why do we do this? And the idea is that you can determine global properties from a local system or from a chart, or not always. So with continuity, that's true. If a local chart is continuous, like a function on a local chart, it's also going to be continuous on the big boy function, but not differentiability or something.
I'm confused. What do you mean by local properties can determine global properties?
Yeah. Like, I mean, if you're trying to define properties to real world objects, it's nice to work with those objects in your maps. Like, for example, like physics problems where you like got a cliff and you throw an object and you calculate where it goes.
Mm-hmm.
It's nice to work on that chart, on the paper chart. It's preferable to do that, or it's actually impossible sometimes to work with the global object, with like the actual thing in front of you. Or how about a really good example is with that example of the thing falling off the cliff, you don't need to care about 3 dimensions. You only care about the representation, like surface representation.
That wouldn't be a chart though.
I think so.
It's not a chart because there's no homeomorphism from R3 to R2. You can't invert like a continuous function from R3 to R2.
Okay, yeah, you're right. So I guess going from 3 coordinates to 2 coordinates is a separate transformation that ends up working out.
It's still like a continuous function. It's just not a homeomorphism.
Yeah. I guess if you think of all of space-time, like when you're doing physics calculations, you don't have to care about all of space-time. You only care about what you care about. Like if I'm doing calculations on like the Eiffel Tower, I don't care what's happening on another galaxy, even though that is a part of space-time. So I do a calculation on the chart that includes only the Eiffel Tower, but then I can extrapolate that result to the real world because of, specifically we know that one of the properties we can extrapolate is continuity, but it's dangerous to extrapolate things.
Honestly, I don't see how that's a chart. Like I see, like technically, if you think of space-time as like a manifold, then yeah, I guess you could view it as a chart. But really,
which it is. It is a manifold.
Right, but practically, because we're on such a small scale, we can just say that we're living in Euclidean space if we're only talking about the Eiffel Tower. if for the purposes of like basic classical mechanics problems, right?
I see.
And so in that case, how would that be like a chart? Wouldn't it just be the space itself?
I think the important thing to realize is if we're trying to model the real world, there is nothing special about Euclidean space. Like it's like that idea of the bird is not impressed. Like the bird is not impressed if you're using coordinate transfer, or if you're using Euclidean space, or if you're using polar coordinates or whatever. Like
but Euclidean, okay.
If you could change the world just by using a different coordinate system, you know, like if I could affect something over there by changing the way I see it, you know, using coordinate systems, like it would, that's terrible. Like that definitely does not happen.
Also, I know this isn't what you meant by there's nothing special about Euclidean space. So this is kind of like a tangent, but I think there actually is something very special about it. Whereas like mainly when you think about like curved spaces, like there are like infinitely many like positively curved spaces and infinitely many like negatively curved. If we're just talking about like purely positive or purely negative, but not like combinations of them. But then there's only like one Euclidean space. It's not like that big of a deal. It's just kind of cool to think about how it's like special in some sense.
Yeah, in that way, but not in the sense that I was talking about.
It's kind of special in the same sense that 0 is special.
Yeah, exactly. Yeah. I'm reminded of something. I think it was somewhere in the lecture where he says, or maybe it was actually in the problem set. They record a video of the solution for the problem set, and the guy mentioned somewhere about differentiable manifolds. How if you're working with 1, 2, or 3D manifolds, there's only one way of established differentiability. If you're working with 5 or above, there's a finite amount of ways of defining differentiability. But if you're working with 4-dimensional manifolds, there are infinitely many, which is unfortunate because we live in a 4D manifold space-time.
I don't actually know what that means, to be honest.
Yeah, I have no clue what just came out of your
mouth.
Okay. No, like I just don't know what it means to define differentiability.
I mean, I briefly watched like the first 5 minutes of the video, and apparently it has something to do with forming a set of all tangent vectors on the manifold. I don't know. It's weird. I was.
Then it's like, if it's the set of all tangent vectors, then wouldn't there be only one? Because it's just all tangent vectors.
I saw an image where it was like a sphere, and then the space they created, or the set they created, were like all of the arrows that are tangent to the sphere somehow.
Tangent space.
Yeah. Oh yeah, that's what it was. That was what it was representing. Anyways, but that's for next week. Oh no. Next week is actually multilinear algebra. This is, in my opinion, like one of the best videos. It cleared up so much for me.
What kind of background does it assume in linear algebra?
Or what we've already done so far.
Really?
Yeah. It's
damn. How do they like? Does he define like vector spaces, then linear trends?
Yes.
How does he do all of that in one video?
Yeah. So he does assume a lot. It's so funny. He has a part at the start of the video where he says, I'm going to be taking advice from Machiavelli in The Prince, where I'm going to be giving you guys no help at all for your intuition. I'm giving you no intuition. So he does not use vectors. He uses polynomials as vectors to teach us vector spaces without thinking of those arrows, because vector spaces are more general, you know?
Yep.
It's very interesting and funny.
Who was I explaining this to the other day? Oh, what? Never mind. This is just like a classmate. I was like,
isn't that just like that's like the first thing they tell you in like your first course in linear algebra, though? Like stop thinking about those arrows.
No, I know, but kids in high school, they're still taught in like physics. Oh, direction.
Yes, arrows. Yeah.
But yeah.
But I find it really funny.
That video.
Yeah, I just find the comparison to Prince of Machiavelli really funny. It's like me and the other teachers have decided to be very mean to you guys and to not give you any intuition at all. I'm like, okay, nice. But in the end,
for your own good, at least.
Yeah. Oh, and at the end, he talks about tensors, which are still a little bit beyond me.
Aren't tensors just multilinear maps? Isn't that what
I have no idea what that means.
It's so matrix is 2D, then just add dimensions to make tensors.
I don't think it's that simple, because
I mean, they represent like transformations in more dimensions, and that's complicated. But if you think of them as blocks of numbers, then yeah.
I guess because everything I feel is interrelated. Like the idea of a covector. Apparently, a lot of things that in physics are covectors without you realizing it. Can't remember off the top of my head. But there's apparently a relationship with vectors and covectors and tensors and taking summations over tensors with vectors and covectors. And
then there's like the definition of tensors is just memed everywhere, where it's like a tensor is something that transforms like a tensor.
Yeah, it's like, come on. So yeah, I'll have to watch that video very carefully.
There was something you said previously that I don't know what you said, like something about like fifth dimension and above. Or
oh yeah. Defining differentiability on manifolds.
That sort of reminded me of like there's like weird strange. It sort of reminds me of two things. One of like the thing where like over fifth degree and there's no formula for the roots of polynomials anymore.
Oh yeah.
And then there was also that thing where it's like, this is probably not related at all, but like your six symmetric group has a strange automorphism group, whereas all the other ones are trivial. That was kind of weird, but
I've not done group theory, so maybe I
automorphism is just isn't an automorphism just an isomorphism to the group itself?
Yeah. So
that's really weird. If that's true, damn.
Yeah. So you have these special groups that are symmetric groups. So think of, if I tell you a symmetric group of order 2, think of it as the set of all permutations on two objects.
Mm-hmm.
So if I say a symmetric group of order 6, think of, I take like 1, 2, 3, 4, 5, 6, then all the ways I could possibly mix them up.
Like by mix them up like in a line, you set them up in a line and you think about all of the ways you could like mix them up.
Exactly.
And then like composing those mixing up. So let's say like one transformation would be taking like 1, 2, 3, 4, 5, 6 and switching the places of 1 and 2. And then another one could be like switching the place of 4 and 6. And then you can compose those to switch 1 and 2 and 4 and 6.
Yeah.
And then like all of those transformations together form a symmetric group of order 6 or degree, whatever.
And imagine you have your set of transformations, and then imagine the set of isomorphisms from the set of transformations into itself. That's called the automorphism on S. In this case, we're talking about S6. And apparently there's something where like all of the automorphism sets on groups, on like all the SNs follow a specific pattern, except for 1, 2, and for some reason 6. And it's
just random, huh?
That's pretty wild.
Yeah.
Wild. Quick question, and then we can go. Where did each of you guys learn group theory? Like from what source?
Textbook. I can send you it. It was a book of abstract algebra by Charles Pinter.
Okay.
Yeah, personally, I'm attending lectures in group theory right now.
Oh, nice.
And my professor has recommended, what is the book? I have it open somewhere.
Artin, possibly, or no?
That's a good question. I don't think I've opened the book.
And also, where are you attending these lectures?
U Ottawa.
Okay, cool.
Abstract Algebra, Theories and Applications, Thomas W. Judson. I'm not doing it for credit though, because the university won't allow me because I don't have the prerequisite courses, which is stupid, but whatever.
Yeah, I think it's
I don't need to do assignments. That's fun.
Yeah.
And where are you planning? Where are you in uni already, or are you still in high school?
I'm in high school. I'm planning on going to either Toronto or Waterloo. I'm still waiting on Waterloo applications. They haven't answered.
Yeah. Wait, did you apply to Waterloo Math?
Yeah.
Oh yeah, I also applied there. Still haven't gotten a response though.
How you feeling about writing the Euclid?
I mean, like I've never really been big on contests, but I think they're fun. Like I've never gone out of my way to like prepare for hours and hours. But yeah, I like doing contests. Like the problems are usually pretty good.
I mean, David's in Waterloo right now. How did you do on the contest? I don't think they actually.
I didn't have to do a contest.
Oh yeah, that's right.
Got canceled.
Oh, yeah. That's right.
Yeah.
Which is good because I would have done not great.
Yo, did you hear how like the math faculty like royally screwed us over? Because last year they let in like way too many people.
2 times. Yeah.
So this year they decreased the number of spots by like a third.
No.
And on top of that, there's 80% more applicants this year.
No.
Oof.
Wait, where'd you hear this?
There's like a Waterloo Discord that I'm a part of, and apparently this is like from an official presentation. And they posted it there.
I wish you guys luck.
Yikes. Okay.
Yeah. So yeah, right. Like last year, people were getting in with like 92s, 90s.
This year it's going to be
it's probably going to be 94 plus at least.
Well,
I think I'm lucky in the sense that Toronto let me in like the first week that I applied. So therefore that's less stress on me because I always have somewhere to go.
Yeah, same.
At the same time.
Nice.
That's terrible.
Like which, like let's say you get into both, which one are you leaning towards?
Oh, just at that point, because it's undergrad, I would just, and they're like pretty similar prestige wise, I would just go for the one that offers more scholarship money.
Oh, nice.
And then for grad research, that's when I would have
probably
to
Toronto
start caring. Yeah, grad, definitely Toronto if I'm staying in Canada.
Yeah, sure.
But Toronto has the Fields Institute though. That's very exciting and like very tempting.
Yeah. So that's the thing, like even if you're an undergrad, just imagine like after your classes you just chill there and like talk to people.
Exactly, right? Yeah. And
that's really cool.
Waterloo has perimeter, but perimeter's physics, right? Yeah,
physics.
Dirty physicists.
Whoa. Got kicked out of the call. I have privilege. Let me just
the recording button is flashing.
That's it. I'm posting it on YouTube. You're gonna be famous.
No.
All right.
Neil deGrasse Tyson's gonna cancel me.
I'll see you guys next week.
See ya.
Yeah.
See ya.
See you guys. Bye.